Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure and honor to welcome Professor Les Ellis to MSR. Les is a distinguished professor at UW. He's been involved in different things. Mainly he's working in signal processing of acoustics. So sound is his specialty, I believe, and sensing that and working on it. So Professor Ellis, please.
Thank you. So I want to mention that this talk that I'm giving is a slightly updated version of a talk I gave a few weeks ago in Cambridge. And it was given to the group of hearing researchers, Brian Moore and his group and other people, Roy Patterson's group at Cambridge, UK. And the reason for that is kind of right here. A Blodell Hearing Research Scholar is something that I was awarded about a year ago, which is gave me some release time and some motivation to work on how the ear works, because people have run into a limit in what they feel the science and mathematics can tell them about the ear, and they wanted some help with that limit. So I also want to thank someone who's been very inspirational in this work, Bishnu et al., who many of you have heard of, and our sponsors. So let me go ahead and get into my first point. And it's really just what I just said, that conventional math tools and science for audio signal representations that we work with now, that we're taught, are insufficient, and they limit our creativity. We're taught a certain set of things. They're a standard part of electrical engineering, computer science, physics, mathematics, and those are limiting. And the better tools in science would give us the ability to, for example, come up with enhanced listening, be it for normal, hearing impaired listeners, or machines, multiple simultaneous sources, noise and reverb. These are standard problems that people face in porting systems from a laboratory to the real world. And let me talk about existence proof that there are better solutions. The first one is we know our ears work well. And we can look at top-down approaches, people like Shihab Sharma or Li Deng or others who work in dynamics. That's essential. Having models of how the sounds evolve over time is absolutely essential part. And I'm not saying that's unimportant. But I'm going to stress something else that's important, which is more the bottom-up feature-based approach. And just from the standpoint of what really can be done if you expand your imagination, you let go of some of your previous notions and previous mathematics, allow for the fact that there might be a different world out there than what we've learned. And I've got a picture here from a recent publication that actually made use of some of our previous concepts, which is a notion of a modulation spectrum and modulation filtering. This is a model of what the ear might be doing, according to McDermott et al., Neuron, and they cited a paper, Transaction Signal Processing, something I've talked about before, called modulation filtering. And their argument, which is an argument that we've gone a bit beyond, and I will be doing that in the rest of my talk, is that, well, first of all, the way that the ear works, it's got a bunch of subbands, and each subband is producing something like a bandpass filter. There's an envelope and compressed nonlinearity. Envelopes come out of every subband. And whenever you talk about an envelope or modulation, there's another word for modulation, which is called product. Modulation, multiply, and product all mean the same thing, which means if you really want to find a modulation envelope, you have to demultiply the original signal, find its carrier, or do something else to get rid of that original carrier. And I'm going to talk about that old communications model, why it's old and why it's a bit dated, and how we can move on from that point. It's a conventional model that people are using. This is a 2011 paper. They got some pretty nice results using something called modulation filtering, which I've argued for previously. But what's really missing...
Experimental work, or is that modern work?
Is what?
Is this experimental work, or is it modern work?
Both.
It's both. Okay.
Both. So in this Neuron paper is both, and you'll find if you look in the literature, you'll certainly see sets of both. But what's missing is part of the scientific community and also the engineering community is people talk about a modulation envelope. And that's a well-accepted concept because the way that the ear works and the way that vocoders work and the way that you can get intelligible speech is about these envelopes, these slow-moving envelopes, one for every subband. You might have 8 or 16 or even 4 subbands. You can excite them with noise, you can get intelligible speech. But when you have 2 talkers, or you have noise, or you have a reverberation going on, that falls apart. So the problems that we started with, which is multiple sources, noise, reverb, are things that don't hold up well to having the envelopes only. So the notion of what's called a temporal fine structure is what the community's after. The problem is they don't have an agreed upon definition. There is kind of an operational definition. I'm going to tell you why that definition is wrong. And I'm going to give you a substitute way of looking at it. Now, let me just give you another existence proof, something that's actually related to this problem. When you go into a new room and you listen to a group of people talking, you can single out a particular talker in a highly reverberant environment like that, understand their speech, even at a negative signal-to-noise ratio. And there's another case of something like that. That's radio frequency, walking around, be it Wi-Fi that's running at 450 or 600 megabits per second, or 4G internet or 3G internet. If you take a look at something which is city kind of layout, that's actually a Wi-Fi record. That's not 4G internet. Little devices that look like this thing that's small on the left. You can get a layout like this between buildings that tells you about how well you'll do. And the key thing about that is when you use Wi-Fi or use 4G internet these days, there's no training sequence. It's a blind equalization that's done. And there's tricks being done in orthogonal frequency division multiplexing that are remarkably similar, as I will argue, to what our ear might be doing. And that's the analogy I'm going to make toward the end of my talk. So let's start heading toward that. And first of all, to get to that point, that final point of OFDM, or frequency division multiplexing, let's start with some history. The idea of breaking things into frequency or subbands, the first person to do it really was Alexander Graham Bell, who tried to send multiple Morse code signals down a single line simultaneous, the multi-user problem for Morse code. He failed in doing that, but by mistake he was able to send voice over that same line. That's called the telephone now. That was in about 1875 that he did that. 1877, Helmholtz ended up writing a book. And a key part of that book is quoted right here. The notion of tones. They used to count 0 crossings if they could. They used to try to make a oscillogram or time domain pictures, but they didn't have a notion of frequency. Didn't link what Fourier did with what happens with sound. It was Helmholtz who made that link. Once we did that, suddenly the area took off. 1906, the notion of product models that are still being used. That's AM radios, initiated back then. 1933, vocoding models, AM and FM together. FM radio came there. And the problem is we're kind of stuck at that 1933 point in terms of the modeling we're using for understanding how the ear works and understanding things like even male-frequency Kepster and what they're doing. Male-frequency Kepster go well beyond what AM-FM models do, but inherent in them, inherent in their formulation, is right there. Let's take a look at something that's more modern. OFDM, and I'm really stressing the FDM part. It doesn't have to be orthogonal. Notion of frequency division multiplexing. That's 1966 is the first papers. I list 1942 because the first person to talk about frequency division multiplexing or spread spectrum in general, Hedy Lamarr, the actress, 1942. And that's used in all modern Wi-Fi, 4G, and high-speed data communications. Now, it's just like this problem we're talking about, multiple talkers. It's called multiple access. Uses reverberation. It doesn't just blindly equalize, it uses reverb to its advantage. In the ways I'm going to show you, without the reverb, there's multiple paths between buildings, it would work worse. It works best if thousands of frequency channels are available for one data stream. The more frequency channels, the better, except for battery life. It's kind of like the ear. We have thousands of frequency channels highly overlapping in the ear. They're not orthogonal. but it offers some novel and surprisingly simple concepts for auditory encoding, whether we're trying to understand what the ear does from a scientific standpoint or come up with new algorithms that are insensitive to noise, can single out sources. Now, what's different about it? It's talking about some communication scheme, but what's the single kernel of difference between what auditory models use and assume, and the stuff I've even talked about before, and what's done in OFDM? Well, it's effect. It's multiple axis, primarily additive. I'm going to show you what I mean by this soon, and not a product model. When people talk about modulation coming out of every subband, and then the fine structure that might be coming at the pitch rate or at a higher frequency rate, they're presuming a product model. That product model causes problems, which I will show. If you use an additive model instead, things get better. Let's take a look at the auditory system, just a simple model of it. And I'm going to keep a simple model from known material, not making any strange speculation here, saying that we have an input signal that's broken into a bunch of subbands. It could be thousands if it's our auditory system. If it's some device, modern audio compression, it might not be thousands. You're limited by computes. But in any case, you have a bunch of subbands that have certain properties. Now, what's special about our auditory system is the hair cell rectification right here. So the hair cell rectification, I'm showing an instantaneous nonlinearity that compresses the signal in a way where if the signal's negative going, it either provides 0 or it lowers the resting rate. So it has a slight amount of negative value, which I'd show by having this white line below the origin. On the right side, we pretty much duplicate the output. Half-wave rectifier, not a perfect model, but pretty much what the transduction between acoustic pressure and neural stimuli does, followed by, now I'm going to foreshadow what's coming, a crummy low-pass filter. If you take a look at every hair cell on the ear, there's several neural fibers coming off it, anywhere between 1 and 8 for the hair cells that go up to the brain. And what comes off them has a low-pass filter, but it's a leaky integrator low-pass filter. Some of those fibers carry information at higher rates than others. Never really been looked at. So let me give you some alternative views. Here's the conventional view of what happens in every subband in our auditory system. Here's the conventional view from the standpoint of auditory research and psychoacoustics. Take a Hilbert transform to form a complex signal called an analytic signal, put things in polar form. Okay, that's where the problem is. You put things in polar form, as you'll see, there's that product. That product's not going to be our friend, as I'm going to show you. Because you start with something which will be a beautiful looking envelope. If you looked at the original signal, two-sided real signal, formed its one-sided analytic complex signal, and then looked at this magnitude, which is again real and non-negative, it's a beautiful looking temporal envelope of the signal. Tracks it really nice. Don't need a low pass when you do this. But then what people do is, so they get some envelope that looks reasonable, non-negative real, and then they take what's left over because that's what you need to put the whole signal back together.
Most of the models that our speech processing people have done, they don't even take the phase, right? They just take the field of back and take the energy as a function of time.
Well, the energy as a function of time would be very similar to this. You put a square there, for example, and low-pass filter it if you wish, if you don't use the analytic signal. But the problem then is all you have are envelopes. Okay, so the standard thing is if you only have envelopes, you don't have what we call the fine structure, which is this branch down here. You're not able to track multiple talkers, not able to track a single talker or noise. These other things that I'm arguing for.
I see. Okay, so you're saying that the phase there.
This is the standard way people go after what they call temporal fine structure. That's a way I'm going to argue against for reasons.
Because most of the models that I have seen simply take, interspike time.
Take what?
The interspike time. There are a lot of spiking, right?
Oh, well, the spiking comes from somewhere, yes. Okay, there's...
Actually, I think I have seen, all the correlation models, that they require the spiking time, whereas they cannot typically be represented by this envelope or the white face. The face they are talking about here.
Well, I'm not going to argue against that, okay?
Okay.
There's issues, but in terms of psychoacoustic experiments these days, and some physiology that's being done with mammals, what Shihab does with Ian Other people at Cambridge do. They do use Hilbert phase. That is the most common thing that's done. The neurophysiologists and psychoacousticians tend to use the Hilbert phase, which is that lower signal. You might be a little uncomfortable with it. I'm sorry, I am too, okay? So that's one example, okay? But here, let me make a more general point, that if you decompose a signal into a slowly varying energetic-like component, multiplied by a finer time structure component, that's still going to be problematic. Any of those, especially if this is unimodular or magnitude equal to 1. Okay? So let's take a look at the alternative. That's the problem. It's a multiplicative view. So what we're going to propose instead is something that's closer to what's done in frequency division multiplexing. We're going to start with rectification. The ear does that. There's certain properties about rectification that are going to be coming soon that you're going to see. Really interesting properties that no one really takes advantage of. That's half-wave rectification. Then what's known as this notion of integration after that, which is a low-pass filter. Now the new part, that top branch is a modulation envelope. Now the new part is, instead of it being a product, it's additive. What we're going to put is what we call a fast envelope. If you're talking about phase locking, you're phase locking to this fast envelope or carrier. It might be at the pitch rate. If it's lower subband in speech, it might be at the input signal rate. So it's addition of the envelope with riding on top of it a much higher frequency. That's a very different model. It's different algebra than we have here. Let's talk a little bit more about this new additive model. So we're talking about the top being something which is identical to the standard half-wave rectified, however you'd like to do it, whether you use a Hilbert envelope or use a rectification followed by a low-pass filter and a real signal. If you look at, for example, Stewart-Rosen's definitions, you tend to have frequencies up to about 50 hertz and below for that envelope, maybe below 16 or 18 hertz in some people's definition. But this new part, which is additive, that bottom fast envelope, starts with a low corner about 50 hertz below the pitch rate, below the lowest pitch, and goes on up to whatever phase locking rate you can have. If you look in the latest edition of Brian's book, you're up to 4 to 5 kilohertz for your phase locking rate. So I'm calling it a bandpass filter just to show it doesn't go on forever. Now let's look at some of these models. The conventional model, I'm using Hilbert phase because that's the most common of people I was talking to in Cambridge, but you can substitute your other favorite product model for the high frequency stuff that you're phase locking to. First problem with it, complex exponential phase. This is a theoretical issue, does not have an inverse function in the standard sense. If you pair it with its original modulation, you're okay. But if you make any change, you're stuck, mathematically or algebraically. The underlying complex polar form's magnitude must always be non-negative. We're going to see the problems that develop, because whenever the real part attempts to dip below 0, you've got a subband of speech coming through bandpass filter. In the ear, in whatever device you're building, it wants to cross 0. It's not non-negative. Whenever it crosses 0, this particular Hilbert phase, or whatever definition you use for a polar form product model, is going to have a problem. It's going to abruptly change its phase by plus or minus pi. That's not connected to any known physiology. And let's contrast this to what I'm proposing instead, which is an additive model, fast envelope. Now there's a deep theory behind it. I didn't pull this out of a hat. And the reason it's connected to frequency division multiplexing and high-speed data communication is something called complementary statistics. If you take a look at, more recently the work of Peter Schreier and Louis Scharf, and before that, Pisson-Bono in France, Transaction Signal Processing 1994, you can see new information and signals that hasn't been used in most audio processing, very rarely used in audio processing. Only papers I've seen are ICAST 2012, maybe one in 2011 that I'm co-author on. Really haven't seen anyone else use it in audio. It's very rarely used for natural signals, in fact. Notional complementary envelope is usually used for complex communication signals, where you have a cluster and a complex plane of 8 or 64 different points in your signal constellation. And because you have this cluster in your complex plane, it's not circular. If you look in the complex plane of the real versus the imaginary part, If you wish to use quadrature, that's fine. There's a pattern which is not exactly circular. If that pattern's not circular, it's got complementary statistics that are meaningful. It's got new information. When speech has periodic correlation, any signal with periodic correlation, could be speech, it could be sonar from a propeller, it has significant complementary statistics.
So is there any argument that this kind of information is connected to auditory physiology at all?
I'm getting there.
Okay, I love it.
I'm getting there, okay. I'm about to get there. A couple of slides. These now make use of a simplified low pass and what I'm arguing for, the additive fast envelope. I'm trying to get at that, okay? When you look at these kind of papers, they're talking about expected values, things that are in the limit, expectations where you have either infinite limits if you assume it's ergodic, or other ways of finding an expected value if it's not ergodic. You also have to assume that signals are harmonizable, other things that you need because they're not necessarily stationary, but yet you need to be able to find some statistics on them. Complicated mathematics, hard to get through with this complementary statistics. What we do instead these days, it's not going to be in my talk, I don't have time for it today, it's a generative model. And what a generative model can do, it's much like having a DFT instead of a power spectral density. If you have a power spectral density, that's a pencil and paper thing. You need to know the underlying true autocorrelation function. You take its Fourier transform, pencil and paper. But if you have data, you can't do that. You do a DFT, you do an FFT, you might window it. You might use linear prediction with other characteristics. Those are all spectral estimators. One estimator of complementary part is this fast envelope. It is an estimator of it. It's not an expected value, it's not a pencil and paper thing, but it works with the data. Let's show you why. This is the slide where I can show you why that's true. This is the only math I'm going to be giving you today. It's actually very interesting. And the reason is, if you take a look at this generative model of what the complementary part is, this new information that has to do with the non-circularity, if you took the analytic signal, the stuff that's really important communication signal, and the reason you get 600 megabits per second. If you look at that, you get a double frequency term where that complementary part is, and the zero frequency term is where the envelope is. The standard envelope is beat by itself down to baseband. Double the frequency that you started with. If your carrier is at 2 kilohertz, at 4 kilohertz is the complementary part. That's what you'd normally get in statistics, in complementary statistics. Now, when you work with a half-wave rectifier, it gets a little more believable and plausible for the auditory system. This is why. Let's assume a sinusoid's coming in. What happens to the Fourier series for a sinusoid? It gets really interesting. If we have a sinusoid coming in, what comes out, this is a sinusoidal input, is a sinusoid at the fundamental frequency. And with a minus pi phase shift in minus quadrature, double frequency term. So here's the story. If you're talking about complementary statistics as new information, it's usually a double frequency term. We know 1.5 kilohertz, 2 kilohertz is important for speech. The double frequency term would be 3 or 4 kilohertz. Hard to argue for phase locking up at those frequencies. Really hard to argue to Brian Moore and his group for phase locking those frequencies, very rare. But if you're right at that 1.5 or 2 kilohertz, it's not so hard anymore. So the stuff that leaks through at the fundamental is right at the frequencies you can get phase locking, which is that complementary information. And by the way, your first harmonic for a sinusoid is in minus quadrature. That's just the nature of the Fourier series. That's just for a sinusoidal input. I can't generalize this for a broadband case because it's nonlinear. But for a narrowband case, it would be like this. The higher order terms for the sine term are very small. Go away basically. The higher order terms for the cosine terms are also quite small, but they don't totally go away. So there's key principles going on here that's linking a fundamental to its harmonic. If we're talking about a subband that's centered at 3 kilohertz for speech, at 6 kilohertz, that first harmonic, there's not going to be much phase locking there, so really not getting much. But if you're talking about something at 800 hertz, 1600 hertz, you will get phase locking, and maybe this guy and this phase shift is important. So let's keep that in mind.
Yeah, actually, just from this method, I couldn't tell that there is a 270-degree phase shift.
Oh, all I did is I just did the algebra. I don't have the derivation on this slide. Okay, I can show you the derivation separately.
Yeah.
Okay, but the derivation is if you start with this as a signal model and then determine A sub k, A0, and B sub k using standard definition of Fourier series, you get these functions that I plotted. So that all that is, it's closed form solution for A sub k and B sub k, even though it's a series, infinite series.
Inverse Fourier series.
Yes. If you use a standard definition of Fourier series, there's a definition of what A sub k is equal to, another definition to what B sub k is. You solve for them, and then you plot them, you get these pictures for this particular S sub t. That's all that is. Okay. So this is the effect of half-wave rectification, which is interesting, a lot more interesting than I would have ever thought. So let's now do some demos that relate to these concepts. What I'm going to do now is I'm going to play two sounds that differ. This is a really crude model of one versus two talkers. And the way I'm going to do this crude model is not really one versus two sources. It's something which is consonant versus dissonant. And the one which is consonant is when they're harmonic. It sounds like one source, no question about it. When they're dissonant or inharmonic, which is the 412 and 740, those two, they don't necessarily sound like one source. They sound kind of like a crummy chord. And what we're going to do is we're going to play them where we play this first one, then the second one. We'll keep looping through. And you'll hear just to hear the difference between them. You're going to listen to them now, and then I'm going to show you the fast and the slow envelope for these. That's what I'm getting to. I'm making the argument the fast envelope tells you the difference between consonants and dissonance, between one source and multiple sources. But let's just start with the test signal so you understand how it hears, how it sounds. That's this one. That one. That one again. Okay. One sounds like a single source. The second one sounds maybe like a train whistle that has two reeds in it. Whatever it is. Not a perfect chord, but certainly more dissonant than the first one. Now let's take a look at these two. If I go with just the first case, which was this one. Not playing. There it is. Just that thing where they're harmonic and sounds like one source. What I'm going to do, for the sake of my discussion, is to talk about half-wave rectification. Start with the usual. Follow it with a low-pass filter. Simplest model, auditorily acceptable to most people. What our auditory system does to find an envelope. I'll call it the slow envelope to distinguish it from the new concept, the additive thing, not a product, the fast envelope. Okay, here's a way to look at it. You can think of the signal that's coming through the half-wave rectifier. And the low-pass filtered version is just following the peaks of it. Okay, because the low-pass filter. What's left over? Bandpass filtered part. It's high enough corner of the bandpass filtered part. These two summed together give you what came out of the half-wave rectifier. Give you everything except the negative going part of the original signal. So what you're doing...
So for the bandpass filter, what is the band frequency?
So for this particular one, I think that what we used here was it the corner 450 for this one?
450 over 2.
450 over 2, okay, so it's halfway.
And then the band?
That's a low corner.
And the upper corner was 3 SC over 2, so 3 times 450 over 2.
Okay.
So you only get that single frequency term.
Right.
Okay.
And likewise for this one, we chose a corner that was made sure that it was flat. And you'll see the results shortly. But I'm going to be comparing the results to this case, which is the inharmonic case. Takes a while to load. Sounds like two things, maybe. Train whistle, at least. We're going to do the same thing for the sake of comparison. This is the more dissonant case, like two sources, maybe. The slow and the fast envelope. And we're going to look at them and compare them. Let's compare the harmonic fast envelopes first. The 300, the 600, clearly harmonic. Here's the fast envelope coming out of the 600 hertz input. Look at its peaks. Line them up. And there's a 300 hertz input fast envelope, perfectly lined up. And the valleys also line up with the peaks of the other one. There's the fast envelope structure, aligns in time. So if I had two subbands, one corresponding to about 300 hertz, another corresponding to about 600 hertz, look at that fast envelope that comes out, call the low-pass filter after the half-wave rectifier a leaky integrator, look at what leaks out, line them up with their phase locking. The phase locking lines up nicely if you correlated the two.
Just a clarifying
Sure.
question, just to make sure I'm following. Aren't those labels flipped? Isn't 600 the one in the top and 300 the one in the bottom?
You're right. Sorry about that.
Never mind.
Okay. I could call this scale and we'd get away with it. Sorry about that. Yes, yeah. That's a mistake. Thank you for pointing that out, Rico. Good eye.
Those envelopes, they line up in the same way the original harmonics that you used to create the sound line up. So what would happen if if the original harmonics would be shifted relative to each other?
So you mean that the original harmonics are all shifted together?
Yeah. So could you go back to the last one?
Okay, because I will be showing you the inharmonic case soon. Okay.
No, I'm talking about the harmonic case.
Okay.
So yeah, hang on please. On the top right you see that, the top right is the sum of the
Yes.
left signals. So
Yeah.
you see that they have been aligned such that peaks of the 300 hertz wave line up with the peaks of the 600 hertz wave.
Yes.
In the same, and of course as a result the envelopes line up in the same way. What would happen if you would shift the 600 hertz wave by say
50 hertz.
whatever?
Both by 50 hertz, you're saying.
No. If you shift it in time by a quarter period or so.
Oh, if there's a relative phase delay between them.
So pretty much I believe this is what makes them to belong to the same, we to perceive them belonging to the same signal. They are in phase. My guess is that if you put, let's say, 37 degrees phase shift, initial phase shift between 300 and 600, we may not perceive.
I think the explanation is different. That particular phase relationship has to do with the fact that they are modeling the output of the half-wave rectifier, right? Because with the half-wave rectifier, the second harmonic, the second peak has to be aligned with the other one to produce the attenuation of the low peak because of the rectification. So
That's a factor. That's a factor. But if we went ahead and did a relative phase, and if you think of what the ear does with the traveling wave, they're not in phase by the time they get to the hair cell.
I would expect
Okay.
either, no matter
so
how
if
you
they
do the
move
same
them
thing.
around, it won't change much our
I don't think so.
Same perception. So
And the
there's,
auditory model will predict that.
Yeah,
The
and so-
logical model will predict the same thing.
Okay.
yeah. And so when I brought this example up to the psychoacoustics and physiology people in Cambridge, it started a discussion that went on for a week. And this is, to me, a success, okay? That's what I wanted to do. I want people to look at things a little
It makes no
differently.
difference whatsoever because all the randomness when you go to the phase, spikes, just swap out all these differences.
You're looking for correlation somewhere else down the line. So if you do a relative phase shift one, and then it's never exact, but you get random firing at the peaks, okay? And if there's some correlation somewhere down the line in this huge structure in the auditory midbrain, it calls these likely from the same source. And all I want to do is contrast. So we could put phase shift in, and we'd get something where they don't line up perfectly in the plot that I showed you. Let's go back to the plot. We'd get something where we don't get exactly this alignment, okay? There'd be a relative phase shift to the bottom one versus the top one, but over time there'd be correlation between the two. And how that correlation is measured is somewhere else up in the auditory midbrain.
And the nucleus will do that already.
Yeah, the cochlear, and then over time, be it 10 milliseconds or 40 milliseconds, those statistics would accumulate and say, hey, we've got one source, because they're firing in synchrony in some way, even though there's a relative delay. Yes?
And the magnitude of these envelopes would also be affected by the relative phase of the original signals?
Nope, here's the magnitude of them right there. They're both
So
slow.
as the signals, as you change the time alignment of the signals, the magnitude of this spectrum stays the same?
The magnitude of each subband output stays the same, okay? The signal itself, of course, if you look at the magnitude of the signal itself before it goes into the individual subbands, of course that's changing. Okay, the signal itself is changing its peaks and its shape. But if you look at the subbands in the auditory system, what's coming out of each one, call it a slow envelope that's defined by a half-wave rectifier and a crummy low-pass filter, but only keeps low frequencies, it's flat as a board, with your phase shift or without it. Okay? And the reason I'm doing this particular case is because when we go to the inharmonic case, the dissonant case next, they're also both going to be flat as a board. So when you look at the standard auditory model of a bunch of subbands followed by a rectifier followed by a low-pass filter, consonant and dissonant shouldn't sound different. They might sound different pitch, but the consonance versus dissonance should not be noticeable. It's something else. What is that something else? Okay, people would argue for the Hilbert phase. I argue against that. In a moment, I'll tell you why. This is the alternative, which is the additive alternative. Now, this is only the harmonic case. Let's go to the inharmonic case. See what happens. Now they're not lined up. No matter what you do with the numbers that we chose, these are never going to line up. You could shift the phase of the top relative to the bottom. They're never going to line up and accumulate their statistics in terms of their, for example, phase locking in such a way that over a period of 20 or 500 milliseconds, you can collect things where they're synchronized. They're always asynchronized, and that's why they sound dissonant. You look at the peaks, too, and the valleys. And we also have, Rico's correct, these are reversed again, so sorry about that. So they're not aligned ever. But look at their slow envelope. No information in the slow envelope per subband. They're both flat, so consonance versus dissonance did not make it through the low pass half-wave rectifier. It's the high pass part, or the band pass part, or the fast envelope as I call it. Okay, so that's one new concept. These are additive concepts. That's another important thing. Let's compare this to the conventional view that's used by psychoacousticians and neurophysiologists. The Hilbert phase is very popular now. And I'm going to give you a different example. Let two tones beat. Sum them together. Let's just play this case. Takes a little while to load. Now this would be considered the case of two tones falling into the same auditory subband. Because they're falling into the same auditory subband, they're beating with each other, and you certainly hear that beating, whatever that envelope rate is that you're staring at. And that's a pretty well understood phenomenon, going all the way back to Helmholtz, that you have an envelope, when you tune a guitar or something like that, you're listening to the beating and waiting for it to go away. When you got frequencies that are close to each other. Now the first kind of hint that there's an issue here is which of the two envelopes is correct, the top one or the bottom one. I don't know. They're both correct. Now let's take a look at that in the frequency domain. They're very close. We presume they're in the same subband, which they would be for our auditory system. Let's look at the conventional Hilbert phase temporal fine structure. The way it's defined is that bottom quantity. It's the cosine of that phase that comes after the analytic signal. We put it in polar form, complex number for polar form. Its phase function, which is a cosine, is between -1 and 1. That's what a cosine is going to give you, whatever phase you put in there. Let's take a look at that signal. That's that same beating signal we just looked at. Let's look at some of its characteristics. Let's zoom in on this portion. After we zoom in on time, I didn't want to use, I told Scott not to use MATLAB's interpolation between points, because there is no interpolation to be done between points. It isn't a vertical line there. That's a discontinuity. So there's something wrong mathematically with this. This definition gives you a discontinuous signal. This is what people are using. And when I get to speech, you're going to see that this is not an artificial case. This happens in speech also. So there's a severe discontinuity, plus minus pi, whenever that thing wanted to cross 0. So let's take a look at the same issue. I argue there's a problem with Hilbert phase and other ways of representing this fine structure. And the problem is fundamentally that whenever your envelope wants to cross 0, you're going to have a discontinuity in any of the standard definitions. What happens with our new fast envelope with this case? Do we still have a discontinuity? Do we have a mess? Let's take a look. Halfway rectifier, slow envelope is just that envelope. There's a fast envelope in blue. Okay, the fast envelope is not magnitude 1. It doesn't go between -1 and 1. It has modulation left on it. That's troubling for some people. That was troubling for me at first because I'm used to this product model. And the product model is where the fine structure has a magnitude that's going between ±1 because you've taken all the modulation out of it. How can you say that the envelope's a modulator if there's still modulation left in what you call the fine structure? I was stuck thinking that way for the last 10 years. I'd argue the community's been stuck thinking that way since the 1920s. Okay? There's no way to force this to go between plus minus 1 without forcing a discontinuity in it. And that discontinuity, as we're going to see, it would exist in speech if you analyze it this way, and it also causes troubles. So here,
Why do psychoacousticians use this model? I never liked this model to begin with. So I totally agree with you. So why do these? So this is not physiological at all. And most of the physiological models I have seen, I mean the good model,
Yeah.
actually is the good spiking information.
well, this is a predecessor to the spiking, okay? This is what comes before the spike. This is what the spiking's based on. I'm not arguing this in place of spiking at all. I'm saying the spiking's got to come from something. What does it come from?
The spiking comes from just physiology. Huh? You
Okay,
put signaling there, they put randomness there, and then people have shown that it does really, really good work. In terms to explain, the sound localization, this coincident detector, all come from spiking. So
I won't argue that, but the psychoacoustic experiments that are being done these days that are looking at
they use that a lot.
are using this, yes. Yeah, 2012 papers are using this, okay? So, but let's zoom in on this portion. What I'm trying to do is give you a good alternative. So what you'll have is people who look at it other ways, but they still look at it in ways where that fine structure before they find the spiking has to go between minus 1 and 1. So it still has to have problems. And I'm arguing you got to get away from that. So here's what happens with the fast envelope when I zoom in on that portion where the envelope crossed 0. Fast envelope just goes to 0 smoothly. There's no discontinuity. There's no trouble. And what I want to get to is the case of speech, because we're going to do the same kind of thing for speech in a moment. So I'm comparing the Hilbert phase version, or any version which is a product form, and its fine structure, before you determine the spiking, with something which we'll call a fast envelope, which is just the stuff that leaks through the leaky integrator that's going on after the half-wave rectifier. And just compare them spectrally. If we look at them spectrally between the two, the red is the Hilbert case spectrally. The blue is the case of the fast envelope. The fast envelope is giving you your two tones exactly. Hilbert phase is giving you all these harmonics, which are distortion products due to that discontinuity. Now, we could compare these two by listening to them, but I think I want to get to the speech looking at the time. Let's take a look at a 1.5 kilohertz subband of speech. We're talking about artificial signals. Does this really matter for speech? And my argument is that yes, it does. Let me just play the speech sample.
A bicycle has 2 wheels.
Let me move ahead. Let's pass that speech sample through a single subband of speech based on, well, the models that they used in Cambridge. And we can just play it after it goes through that subband. .5 kilohertz, it sounds squeaky, but you can hear some of the speech coming through just that subband. Now let's take a look at our various representations. Hilbert phase. There's the original signal in purple coming through there. Not the original signal, but after the subband is in purple right there. Its Hilbert envelope is the black dashed line. Beautiful looking temporal envelope. These are time signals. There's a Hilbert phase for speech. What did it do? Pretty ugly. This is any definition that's assuming a product form where that fine structure has to go between -1 and 1. If your spiking follows it, fine, but any model that does that is going to have these problems. Let's zoom in on some portions. Discontinuity right there. Let's zoom in when it gets small. When the magnitude gets small of the signal, got some problems. What this does right in this portion, not a function of the signal, it's a function of the word size of your computer. Really, what it's doing here. Because they're down at a very small signal level and we're looking for a transcendental function, inverse tangent. So, the Hilbert temporal fine structure, which pretty much everyone's using in psychoacoustics and a lot of physiologists are using as a predecessor for the spiking model, has artifacts. It's because it's of constant amplitude, even at times when the artifacts are pronounced, and that's fundamentally because of the product model. It's also not terribly physiological using this. So the fast envelope fine structures are our alternative that doesn't have these mathematical problems and also is more physiological. Let's do the same experiment. There's a Hilbert phase temporal fine structure that would come out. If we use a half-wave rectifier instead, let's look at the fast envelope. Fast envelope is, I'll zoom in on the difference. The Hilbert is the red. Conventional is red. Product model is red. Our fast envelope is the blue one right there. Has no discontinuity.
That this fast envelope can capture the carrier somehow?
That's exactly what it is. Capturing both the pitch and the carrier. Depends where you put that low pass corner.
But typically in communication, signal processing one carrier is a constant frequency in the cosine side. But here, carrier changes the function time in terms of.
We have to have it that way, otherwise we're going to get artifacts. Now, those artifacts you get in man-made communication signals are the message that's being sent. Okay? Here, we don't have such a clean message that was man-made. So that's why it's a problem to use those communication ideas for natural signals. There's nothing that's doing, for example, phase shift keying coming from our auditory system that we have control over. Okay? So if we make a receiver look for that, it's going to see artifacts which were zero crossing.
Also to argue that the slope envelope is analogous to the message that gets sent.
The slope?
I mean, in man-made communication system,
Yeah.
you get constant envelope fast, with a carrier.
Yes.
And then you get a message that get multiplied. But now for this natural signal,
Yes.
so what is the analogy here? Do you try to make analogy that the fast envelope is like, distorted version of the carrier, and the slow envelope gives the message?
Here's the closest I can answer that. The experiments are in progress right now. Okay, they're working with guinea pigs. They're looking at this model and comparing it to Hilbert phase in Cambridge right now. The model that we're using is one, we're comparing the red for where the spikes are. The probability of a spike is highest at the peaks of the red. That's the old model, okay? The new model says the probability is where the peaks in the blue are. But if the peak is very small, it's a lower probability. That's all. So what we're saying is we're still phase locking, but when the signal level is small or crossing zero, the probability of phase locking at that phase drops down. That's all.
So you can simulate using this one as a probability,
Yes,
and then
yeah.
compare with the spiking result
Yes.
experimentally to see how much coincidence you might get.
Yes.
Okay, that's cool.
And that
Nothing has been published on that?
No.
Good. Oh.
No, by December, well, the results will be ready by the end of it, probably paper ready by December, a
Who are
draft.
doing experiment to verify that?
Excuse me?
Who are doing experiment measurement to see whether using this model as a probability, you can generate the spikes that are consistent in terms of statistics with the real?
Mike Stone and his colleagues in Cambridge. Okay, and physiology people from the neurophysiology department, Ian, I forget his last name, his first name's Ian, who I was there with. They're working with guinea pigs and looking at single in the inferior colliculus and lower level cochlear nucleus.
But in the cochlear, in the ear, you probably wouldn't see that one. You probably have to go a little bit higher level.
You can't really get to the fibers coming off the hair cells. My argument would be in the fibers, the 8 or so fibers coming off each hair cell, each outer hair cell, you might see something that spikes at the peaks of the blue. So here's a way to look at it. Spike probability is high here. It's pretty high here, but it's higher here than it is here. That's an example.
That's really cool.
Okay, so it's a model that doesn't mathematically break. If you followed the red and spike at every peak of the red, what's going to happen here? Big spike here, what happens there? It's meaningless. Okay, so when you look at the results that people try to predict what the physiology is doing when they use a Hilbert phase or other measures that are going between +1 and -1 with the product model, they don't work so well. Okay? That's really not a big change. Now there's a little more on this. We could listen to these, and if you listen to the Hilbert phase, it sounds horrible, all clicky and stuff. You listen to the fast envelope, it's much closer to intelligible, doesn't have the distortion. That should be obvious. But a few last points I want to make. We have all these subbands in the ear, and I want to get back to what, an application of this could be. And on the right-hand side is a really interesting one. We don't necessarily, with OFDM, or orthogonal frequency division multiplexing, we do blind equalization. In fact, if you walk around holding a Wi-Fi or cell phone or something like that, the reverb helps you. Why does it help you? Well, we look at a couple different frequencies. And if we're at frequency 1, some subband, and the direct and, for a strongest reflected path, add out of phase, ignore that subband, it's weak, or weight a lot less. Whereas if you're at some other frequency and just the distances of these are just right, the timing of them just right, you get constructive interference, not destructive like you do for frequency 1. So if you look at a whole bunch of frequencies divided up into a bunch of orthogonal frequencies, which is what they do in OFDM, you're going to get something that does much better. As you walk around, it's automatically scanning over the frequencies. Now, there's other things like it's orthogonal, which the ear isn't. There's a carrier channel coming through, which the ear doesn't necessarily directly have. I'm just arguing for this kind of analogy, and also carrier recovery issues, a little more complicated than that. So, we can compare what we have. This is kind of for Malcolm's purpose. What's the difference between what we're arguing for now, which is this fast envelope, versus, say, Malcolm Slaney's corellogram? In a corellogram, you're looking for this kind of information by doing correlations, what's coming out of every subband, where this axis, this is the frequency subband, this axis over here is autocorrelation lag. And let's just contrast those two. In a corellogram, you've got perfect symmetry about the center points of autocorrelation, perfect symmetry right here and here, slight amount of time variation. In this case over here, we don't have the exact perfect symmetry, but there's a much bigger difference. This picture is all non-negative real. Okay? This corellogram is all non-negative real. This picture on the left can go negative. Okay? And what's happening here with the picture on the left is everything that's blue is a zero crossing. And that zero crossing and that asymmetry is a very different representation. Thing on the right is a square, is a quadratic version of the signal. Thing on the left, there is a rectifier in there, but there is a potential for it to be closer to holding superposition.
Yeah, so this is for one segment, the vowel? Or
yes,
something?
yeah.
It's a steady state sound, right? If it's not stationary, you have to change over time.
Single to speaker, one segment of a vowel, about 6-7 pitch periods.
Okay. But the time is different, right? The corellogram, the axis is the time delay.
This is samples here. And this is time in milliseconds, yes.
Oh.
So they're not the same.
They're not the same.
They're both time, but different units of time.
Actually, can you plot that fast envelopegram something also in the same way that you do correlation?
Oh, it kind of is here. The only difference is that this is sample index, and this is actually, Scott converted this to actual time in milliseconds. So they really are equivalent. The duration of the left one and the right one, they're pretty close, not exact. But they really have the same time axis, it's just the units are different in this plot.
There is a straightforward mapping in Malcolm's toolbox for the channel and frequency. So.
Yeah, there is a straightforward mapping. There's a straightforward mapping of this axis to that axis. Yeah. These axes are identical, but the axis coming out of the screen, okay? The dependent variable is wildly different. That's the big difference.
How do you experimentally verify which one is more realistic?
Well, I really don't know what to do with these, but the physiological experiments that are going on in Cambridge right now are trying to confirm whether that fast envelope does a better job of predicting phase locking for signals that are, for example, beating, and he's also using chirp sounds from guinea pigs, their natural vocalizations, a set of signals that have characteristics of the things I've demonstrated for you. I can make a few more summaries here. The main point I'm making is that the envelope and its fine structure, which I call TFS for temporal fine structure, are additive and not multiplicative. You don't have the problems if they're additive. You're not forcing the temporal fine structure to have these discontinuities or strange behavior. Additivity is an easier decomposition to work with. If you align fast envelopes, it's a good way to do segregation. We can allow, for example, an observation that happens in the auditory system is that neighboring subbands in speech that overlap heavily allow for sharper tuning curves for loud sounds. How does that happen? Well, allowing the fast envelopes to be additive can reinforce the tuning curves or the narrowness of a subband, which is actually quite narrow in the auditory system. And all of this is something called frequency diversity. It's potentially a new view of pitch modeling. I was talking to Bob Carline about this when I was in Cambridge. There's need for something more general than autocorrelation features. And this is when Bob and I talked, and when I was talking about the corellogram, There's a couple things the correlogram doesn't predict that happen. One is that the correlogram is not sensitive to forward versus backward order. You could take a signal and reverse its order. Correlogram doesn't change. Okay, assuming the signal is, for example, a steady vowel. If you reverse it, the correlogram is identical, whereas what we're showing with the fast envelope, it changes. And even a transient signal, if we reverse its order, correlogram over a certain interval will not change. Roy Patterson's auditory image. This is another person who was at Cambridge that I worked with. He talks about a stabilized image, and what we're talking about with the fast envelope is a computationally or mathematically defined way of doing what he calls an auditory image. Better potential for analysis than Hilbert or other product models. The fact that it's an additive model means that he can decompose it. So that's it. I'm done with 2 minutes left. Thank you.
Can you say something about how this bandwidth, bandpass filter is computed according to the theory?
Okay. You know, I don't want to fix on any two frequency endpoints, but let's just say the lowest frequency of the bandpass filter is just lower than the lowest pitch you'd ever get. Because you want to capture the pitch period, in speech that is, you want to capture your periodicity of your pitch. So let's make it 50 hertz or 70 hertz or something like that. Let's let its highest frequency capture the fastest phase locking, whatever mammalian species you're working with. You know, cats phase lock at a higher frequency than humans do. So whatever your phase locking of humans gets argued between 1.5 kilohertz up to 8 kilohertz, somewhere in that range for the high end. So it's basically everything outside of that low frequency envelope.
You know, how big it is, as long as
It can be large, yes. Okay, now there's going to be a certain subbandwidth you start with, which is of course going to limit it in terms
does
of.
it come from this complementary?
It's
phase
all the
information?
complementary information is in the fast envelope. But let me be a little more clear about what the theory of complementary statistics. Okay, everything that's down in the slow envelope is the circular or non-complementary part. There's nothing which is complementary in the slow envelope. It's all left out. But when you go to the fast envelope, you have both. You have a mixture of both. That's what the theory says, and that's what you get in practice. That's a fancy way of saying that when you look at that fast envelope, it still has modulation on top of it. But it's got other information buried in there that you wouldn't have had in that slow envelope.
Okay, so going back to my original question there.
Yeah.
Which information do you consider as a message, and which information do you consider as carrier? And do you mix them together, or do you consider them to be separate as in the engineering?
You know, I would have to say that, you know, in terms of how the ear works, for example, or how a speech recognizer should work, you should use both. Okay, both the best you can. Why throw out any of it? Okay, but you can. But if you have pristine conditions, that is one talker, high SNR, you can use only the envelope and use noise as a carrier. That's Bob Shannon's experiment. That was in Science. 8 subbands, you get intelligible speech. You throw some noise in there, you have a lower SNR, it falls apart. You throw 2 talkers in, it falls apart. What does that suggest? It suggests that this fast envelope is needed for noise, for multiple talkers, or for reverb, the things that would make the noise-excited vocoder break down.
Thank you very much, Les, for the wonderful talk. Let's thank the speaker.